time to analyze a perfectly elastic collision. So in a perfectly elastic collision, kinetic energy is conserved. This is what makes the collision perfectly elastic. As mentioned in the reading, is mostly a model. Let's see how to approach it and see what it looks like. So this is the nuclear reactor problem. Let's see what we had. We had a hydrogen atom. Let's call it H. Mass is given in atomic units. We're not going to use kilograms. The numbers are so tiny. It doesn't matter, whatever, as long as we have a consistent mass. So M1 was given as 1 unit. Moving in the plus x direction at this nice large velocity, V10, 1930 meters per second, which then makes this positive x. Collides with a neutron, also of mass 1 unit. Because they're the same mass, it doesn't matter. That has no bearing on the fact that the collision is going to be elastic. Mass has no bearing on the elasticity of the collision. But we'll see something interesting because they have the same mass, but it does not make it perfectly elastic. Again, 1 unit. Moving in the negative x direction at 2980. So it's moving this way. V2 initial, 2980 meters per second. And now look what happens. You are simply told after collision, here's what's going on. You're not told they stick together, so that means the objects are still separate. You still have a hydrogen atom, you still have a neutron, and they still have the same masses. None of those changed. And we don't know anything. We don't know V1 final or V2 final. But let's set the equation up and see what happens. This looks very much like a general momentum setup, and it is. It's very, very similar. Pi equals Pf. M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. So yes, we could put numbers in now. But before we do that, let's just take a look and see what we have. Notice the masses. All the masses are identical. Not the fact that they're just 1, the fact that M1 equals M2. For this problem, that means they cancel out. They can be factored out, therefore they cancel. This will not happen all the time. This will only happen if the masses are the same. And once again, every perfectly elastic collision doesn't have identical masses, just for this problem. So now we can put numbers in. 1930 meters per second plus negative 2980 meters per second equals V1 final plus V2 final, or negative 1050 meters per second equals V1 final plus V2 final. Looks like we have a problem because we have 2 unknowns. In fact, if this was only a general collision and this was the only data we had, the problem was unsolvable. However, you are told the collision is perfectly elastic. Since we are told that, we do have another equation we can use. We'll see what it looks like and then decide we never, ever, ever want to use it again. The other equation says this. KE initial equals KE final. Now remember, KEs have masses and velocities in them, just like momentum, so we'll have similar unknowns. Let's see what this equation would look like if we had to use it. 1/2 M1 V1 initial squared plus 1/2 M2 V2 initial squared. That's the initial kinetic energy. 1/2 M1 V1 final squared plus 1/2 M2 V2 final squared. Now, no matter what, the 1/2s would cancel. And for this problem, and this problem only, since the masses are identical, the masses would cancel. So take a look what you got left. V1 initial squared, so we can at least see what it would look like. 1930 meters per second squared plus negative 2980 meters per second squared would be V1 final squared plus V2 final squared. So we actually do have two equations and two unknowns, the same two unknowns. But what we would have to do is what we normally do, substitute one into the other. That means probably solving, let's call this equation 1 for either V1 final or V2 final. Substituting in, squaring it. All right, when we square it, we'd have to FOIL, then we'd have a quadratic, and then we'd have to solve it. All we can say is, boo, too much work. So somebody smarter than us decided to take an analysis of this equation. And when they looked at KEI and KEF and the conservation of momentum equation and combined them and manipulated them, person came up and said, I have an equation that will accomplish the same goal to solve this problem and is still based on the fact that kinetic energy is conserved. So this equation can only be used for perfectly elastic collisions, and it is never the first equation you start with. It is called the velocity equation for perfectly elastic collisions. And it is expressed a number of different ways, but when it is derived, which we're not going to do, this is what it looks like. Now, once again, this can only be used for perfectly elastic collisions. If you're not told it's perfectly elastic, don't touch it. And it should never be the first equation you start with. But here's what it looks like. V1 initial plus V1 final equals V2 final plus V2 initial. That is how it usually is derived out. It could be written V1 initial plus V1 final is V2 initial plus V2 final. It doesn't matter. You get the V1s on one side, the V2s on another side. This is the second equation for perfectly elastic. So let's substitute our numbers in for this problem. So let's see what we would have. 1930 meters per second plus V1 final equals V2 final plus negative 2980 meters per second. So we could solve this for either V1 final or V2 final. Let's solve this for V2 final. It would be 4910 meters per second plus V1 final. So look, here is our second equation. I'm not going to go through and solve it out. These are simultaneous equations which we've looked at. Here are the two equations. They have the same two unknowns, and you can solve them. I'm going to give you the answers. When you solve, here's what you will get for V1 final. Negative 2980 meters per second. Here's what you will get for V2 final. 1930 meters per second. You can verify these are the two answers. In this case, something interesting happened. If you notice, after collision, the particles exchanged velocities. This will not always happen. This is a very specific case of perfectly elastic. So again, masses don't make it elastic. Exchanging velocities don't make it elastic. And every perfectly elastic collision will not exchange velocities. This will occur if the collision is perfectly elastic and the objects have identical masses. Then they will exchange velocities. Otherwise, they will not. Again, you can have perfectly elastic collisions with objects of non-identical mass. In fact, there will be homework problems relating to it. Just remember, they will not exchange. You have to go through the simultaneous equations and the math. This is just a fact that can be used if you notice it. So it will also save you on one homework problem so you don't have to solve like 5 different problems. If you notice this fact, it'll make your life easier.